Going on, guys? Let's look at this problem right here. Here this question is asking two thin lenses having focal lengths of 15 cm and negative 15 cm are positioned 60 cm apart. A page of print is held 25 cm in front of the positive lens. Describe in detail the image of the print. Okay, so before we do this problem, let's go ahead and draw a sample diagram. First lens is a positive focal length lens. It means it's a converging lens, right? Converging lens. And the second lens is negative focal length lens, so that's going to be a diverging lens. And here we have f1 is equal to 15, and then f2 is equal to negative 15 centimeter, and then they have mentioned the distance between these two lenses is 60 centimeter. So this distance from here to here is 60 centimeter, and then we have the page. A page of print is held 25 centimeter in front of the positive lens. Okay, so this is our positive lens. Okay, and we have a page that is placed 25 centimeter in front of the positive lens. So this is going to be 25 centimeter from the positive lens. And the question is asking, describe in detail the image of the print. Okay, now let's go ahead and see what's going to be the image distance due to the first lens. To find that one, we can use this thin lens formula. 1 over f1 is equal to 1 over so1 plus 1 over si2. Okay, so before we do this problem, let's note down the information for this question. f1 is equal to 15 centimeter and the object distance is 25 centimeters. So so1 is equal to 25 centimeter, and here what we are trying to find is we are trying to find the image distance. That's our question. Okay, so if we rearrange this equation, that's going to give us 1 over si2 is equal to 1 over f1 minus 1 over so2, and we know the focal length, that is 15 centimeters. So this is going to be 1 over 15 minus, and the object distance is 25, so this is going to be 1 over 25, and here we can take the common denominator as 75. If we take 75 as a common denominator, this is going to be 5 right here, and this is going to be 3, and that's going to give us 2 over 75. And this is 1 over si2. They have si1 actually, si1, because we are trying to find the image distance due to the first lens. So this is si1, and then 1 over si1 is 2 over 75. Therefore si1 is going to be equivalent to 75 divided by 2, and that is equivalent to 37.5. Okay, so this information is necessary, and we know that this is a real image because we are getting a positive image distance. So this is going to be real image. So if this is a real image, it means this is coming, this image is behind the lens. So behind the lens, this is 37.5 centimeter. So from here to here is 37.5, and the total distance between these two lenses is 60 centimeter, right? So this distance is going to be 22.5, because we need this information, because for the second lens this image is going to be the object, so we have to use this distance. And also to find whether this image is inverted or upright, we can use this magnification formula, that is m is equal to negative si over so, and we found out the image distance, that is 37.5. so this is going to be negative 37.5, and the object distance was 25. Okay, and if we 25 is multiplication of 12.5 times 2, so this is going to be 2, and this is multiplication of 12.5 times 3, so negative 3 by 2, that's going to give us negative 1.5. Since we are getting the negative answer, this means this image is inverted. So this image is going to look like this down, right? Now we have the information due to the first lens. Now let's go ahead and find the information due to the second lens. Now for the second lens, the object distance is 22.5 centimeter, and that is in front of the lens, so the object distance is going to be positive. So let's say so2, and that's going to be positive 22.5. And here we are trying to find the image distance, and the focal length of the second lens is given by negative 15 centimeter. So this is going to, f2 is going to be equal to negative 15 centimeter. And let's again, we can use the same equation, that is 1 over f1 is equal to 1 over f2 is equal to 1 over SO2 plus 1 over SI2. Here we are trying to find the SI2. So if I rearrange this equation, that's going to give us 1 over SI2 is equal to 1 over F2 minus 1 over SO2. Okay, now let's go ahead and plug the values. The first value, we have the focal length is negative 15. So this is going to be negative 1 over 15 minus the object distance is going to be 22.5. So this is going to be 1 over 22.5. And here we can take 45 as our common denominator. And to avoid confusion, what I'm going to do is I'm going to multiply this one both side by negative 1. So in that way we will get negative 1 over SI2, and in the other side all of them are going to be positive. We will get 1 over 15 plus 1 over 22.5. Now we need some space, so let's get rid of this part. I'm going to note this one down in the other side because we need all the detail about the image information. So we are going to note this one down right here. Let's get rid of this one. Okay, so I'm going to just copy this one down right here. SI1 is equal to 37.5, and it is a real image, and we found out the magnification, that is negative 1.5. This means the image was inverted due to the first lens. Inverted. Okay, so this is the image, detailed about the image due to the first lens. Now we are continuing this about the second lens here. Let's finish that one. So I'm going to erase this one, and let's continue here. Okay, negative 1 over SI2 is equal to this one, and we can take 45 as a common denominator. If we take 45 common denominator, this is going to be 3, and here we are going to have 2, and this is going to be 5 over 45. 5 over 45 is 1 over 9, and this is negative 1 over SI2. Therefore SI2 is going to be equal to negative 9. And since we are getting the negative answer, this is a virtual image, right? Virtual image. So virtual image means this image is going to form in front of the lens. So this is going to form in front of the lens, and let's see what else we can find out from this. And also we can find the magnification. M is equal to negative SI over SO, and here we know the image distance is negative 9. Negative 9 divided by the object distance, that is 22.5. Okay, so 22.5 is 9, and 22.5 are multiplication of 4.5, and 9 is multiplication of 2 times 4.5, and 22.5 is multiplication of 5 times 2.5, right? So 2 divided by 5, and 2 divided by 5 is same as 4 divided by 10, that's going to be 0.4. And since we are getting the positive magnification, this means this is upright. But however, we use this image, it was inverted, that was our object, right? So this is positive, but the object we took is inverted. So this is same same direction as the object. Since the object is inverted, this image also inverted, right? So this is the magnification related to the object. So here the object is image. Now the real object is right here. So due to the real object, we have to find that one. What we can do is mt is equal to m1 times m2, right? m1 is negative 1.5 and m2 is this one. Okay, and m1 is negative 1.5 and this is 0.4, and that's going to give us negative 0.6, negative 0.6. So this means the image is inverted, right? Inverted due to the related to the object, and it is 0.6 times, like it's smaller than the object. And let's get clear about this magnification. The first magnification is related to the real object. So this is our real object, that is negative 1.5, and that is inverted. So we had that image right here, and this image was the object for the second lens, right? And since this is the object, the magnification we found out is this one is respect to the image, okay, related to the first image. So this magnification related to the first image. Now to find the magnification related to the real object, we use this equation, m total is equal to m1 times m2, and that gave us this one. So from this one we know that the final image is going to be inverted respect to the object, right? And it is smaller, and also the image is virtual. And these are the information we know about the final image, and that's how we do this kind of problems. I hope this helps. Thanks for watching.